We are now discussing Lab 8 implementing logistic regression in Python. This code snippet uses the pandas library in Python. To load and display a dataset, let's break down each line. Step number 1. Importing pandas. Import pandas as PD. This line imports the pandas library, which is a powerful tool for data manipulation and analysis in Python. It allows as PD for easier use throughout the code. Second step is defining column names. Columns is equal to age, work class, FNL, WGT, education name, martial status, occupation, relationship, race, sex, capital gain, capital loss, hours per week, NAID, country income. This line creates a list called columns containing the names of the columns in the dataset. Note the use of education name and hours per week and native country. The extra tab character might be a result of copy-pasting issues. Removing the tabs would improve the code's readability and reduce potential errors. Step 3. Loading the dataset. Data is equal to PD, read CSV, output.data, names is equal to columns, set is equal to S, NA, values is equal to, engine is equal to Python. This is the core of the code. It uses PD, read, CSV to read a CSV comma separated values, file name, and pandas data frame called data, presumably containing information related to income prediction. Let's break down each step. Step 1. Check for missing values. Print data is null, sum. This line calculates the sum of missing values, none or not a number, in each column of the data frame is null. Creates a Boolean data frame indicating where values are missing, and sum adds up the true values representing missing data in each column. The output shows the number of missing values per column, allowing you to assess the extent of missing data. Step 2. Drop rows with missing values. Data is equal to DT, drop NA. This line removes any rows containing at least one missing values. Drop NA is a simple but potentially loosey method. If the missing data is significant or not randomly distributed, this could be biased your result. More sophisticated imputation techniques, filling in missing values based on other data, might be preferable in many cases. Step 3. Convert categorical columns to numerical using one-hot encoding. Data is equal to PD get dummies. Data drop words is equal to true. This line converts categorical features, variables with non-numerical values like male or female, into numerical representations suitable for machine learning algorithms. One-hot encoding creates new binary columns for each category within a categorical feature. For example, if you have a gender column with male and female, it creates two new columns, gender male, one if male, zero otherwise, and gender female, one if female, zero otherwise. Drop words true prevents multicollinearity by dropping the first creative dummy variable. This is because the remaining dummy variables can perfectly predict the drop one. For example, if you have only gender male, you know gender female is 0. If gender male is 1 and vice versa. Step 4. Split the data into features and target. X is equal to drop, data drop, income 50k, access is equal to 1. Y is equal to data, income 50k. This final step separates the dataset into features X and the target variable Y. X is equal to data drop, income 50k, access is equal to 1. This line assigns the column except income 50k to X. There are the predictor variables used to predict income, access is equal to 1. It specifies that we are dropping a column. Y is equal to data, income 50k. This line assigns the income 50k column to Y. This is the target variable, what we're trying to predict whether income is greater than 50k. This code snippet uses the train test split function from sklearn to divide the dataset into training and testing sets. Let's break down it step by step. Step 1. Import train test split. From sklearn model selection, import train test split. This line imports the necessary function from the sklearn library. Train test split is a crucial tool for evaluating the performance of machine learning models. Step 2. Split the data. X train, X test, Y train, Y test is equal to train test split XY. Test size is equal to 0.3. Random state is equal to 42. This line performs the actual split. Let's examine the parameters. X. This is your feature matrix, the independent variables. Y. This is your target variable, the dependent variable you're trying to predict. Test size is equal to 0.3. This parameter specifies the proportion of the data to include in the test split. In this case, 30% of the data will be used for testing and the remaining 70% will be used for training. Random state equals to 42. This parameter sets the seed for the random number generator. This ensures the split is reproducible. If you use the same random state value, you'll get the same train test split every time you run the code. Without a random state, the split will be different each other each time potentially leading to consistent result. The function returns four arrays: x train, the training set features; x test, the testing set features; y train, the training set target variable; y test, the testing set target variable. The split is done randomly, but the random state guarantees that the random split is consistent across multiple runs. This is essential for reproducibility and comparing different models fairly. Without a fixed random state, each one would produce a different training and testing set, making it difficult to compare the performance of different models. This code trains a logistic regression model using the logistic regression class from sklearn. sklearn. Let's go through each step. Step 1. Import logistic regression. From sklearn linear model import logistic regression. This line imports the logistic regression class, which is the core component for building a logistic regression model. Sklearn provides a convenient and efficient implementation. Step 2. Create the model. Model is equal to logistic regression max iter 1000. This line creates an instance of the logistic regression class. The max iter 1000 parameter sets the maximum number of iterations the algorithm will run to find the optimal solution. Increasing max iteration can help the algorithm coverage if it's not reaching convergence with the default value, but excessively large values can increase computation time unnecessarily. The default is often sufficient, but in cases where the model doesn't converge, indicated by a warning message, increasing max ITR can be a solution. Step 3. Train the model. Model fit X train, Y train. This line trains the logistic regression model using the training data. X train, the feature matrix from the training set. Y train, the target variable vector from the training set. The fit method learns the model parameter coefficient and intercept by finding the best fit to the training data, aiming to minimize the log loss function. This process involves iterative optimization algorithm. This code evaluates the performance of a trained logistic regression model using several common metrics. Let's break down each part. Step 1. Import metrics functions. From sklearn metrics, import accuracy score, confusion matrix, classification report. This line imports three essential functions from sklearn metrics module. Accuracy score calculates the accuracy of the model, the percentage of correctly classified instances. Confusion matrix creates a confusion matrix which shows the count of true negative, false positive, and false negative predictions. Classification report generates a classification report containing precision, recall, F1 score, and supports each class. Step 2. Make predictions. Y prad is equal to model predict X test. This line uses the trained model to make prediction on the test set features X test. Model prediction returns an array or predict target variable values y prad. Step 3. Evaluate the model. Accuracy is equal to accuracy score y test y prad. Con matrix is equal to confusion matrix y test y prad. Class report is equal to classification report y test y prad. This line calculates the evaluation matrix. Accuracy is equal to accuracy score y test y pred. Computes the accuracy by comparing the predicted values y pred to the true values y test. Con matrix is equal to confusion matrix y test y pred. Generates a confusion matrix visualizing the model's performance by showing the count of correct and incorrect prediction for each class. Class report is equal to classification report y test y pred. Produces a classification report providing precision, recall, F1 score, and support each class. Precision measures the accuracy of positive prediction. Recall measures the ability to find all positive instances, and the F1 score balance precision and recall. Support refers to the number of actual instances in each class. Step 4. Print the result. Print accuracy, print confusion matrix and con matrix, print classification report, and class report. This line print the calculated metrics in user-friendly format. The output provides a comprehensive evaluation of the model's performance on the test set.